everyone, welcome to this week's latest in Bitcoin tech. This week, we'll try to understand, if not entirely, at least the contours of what BIP-324 is about. Why is it being worked on currently? It has something to do with quantum threat. So that's why people are looking into it. So we'll understand what it is, how it works, and where the threat actually is with respect to quantum computers. And we'll briefly look at what are all the solutions that are being developed. Definitely not an exhaustive deep dive into the solution because it it goes into the depths of post quantum cryptography. We'll just uh, learn about some terms. That's the best we can do. Uh, at least that's the best I can do now. Okay, so BIP-324 is all about the P2P messaging protocol that happens between two nodes. Um, So, so BIP-324 came is actually the version two of the transport protocol between nodes. It came into being because of the limitations associated with V1 itself. So basically, um, if we look into the basic interaction between two nodes. The top one is V1 and the bottom one is V2 in this illustration. So when Alice connects to Bob, she will be sending a stream of requests uh, pertaining to or sticking to the transport P2P protocol that the Bitcoin uh, core recognizes or uses to establish and exchange information between nodes. So, so all this request replies and everything was happening in clear text. So, if there is an observer, of course, every connection goes through an ISP, and if the ISP deems so, he can analyze these exchanges between Alice and Bob and establish that Alice is running the Bitcoin protocol and Bob is also running the Bitcoin protocol, and both are exchanging messages at a very top level. If he wishes to or inspects the package, a lot of other information can also be revealed. We'll look into what those informations are in the following slides. So, so what 324 does is that it merely encrypts this whole set of exchanges or exchanges happening between Alice and Bob. So it is just for illustration. It happens both ways. Alice, Bob, Bob, Alice. If there is somebody in between, Carol, then that also gets encrypted. So it's a full encryption protocol. So that's what the purpose of V2 is all about, primarily to encrypt the traffic, and it also serves to protect the message integrity. So once it is encrypted, of course, Bob will come to know if someone has tried to modify it, attack it. There are mechanisms that Bob can use to identify such attacks, and Bob can also have abilities to resiliently error correct between error correct the packets that he received. So that's basically the purpose behind BIP-324 itself. So largely the functions of BIP-324 means how it goes about doing all these things is that there is a key exchange part happening, then there is a shared secret derivation happening, and then packet encryption, and all other things. So these things will look into in detailed in the BIP-324 working section. So we saw that V1 is clear text. So we'll briefly look at what kind of information was exposed uh, in V1. So to begin with, a V1 header will look like this. Means before BIP-324, when Alice's node talks to Bob's node, he will send these series of data. First will be the network magic 4 bytes, then typically a command name and the payload length, checksum bytes, and followed by the payload itself. So when an observer or an attacker intercepts this header, he can observe a bunch of things. He comes to know primarily that Alice and Bob are talking about Bitcoin itself. And from the network magic itself, he can infer information such as what type of network it is, mainnet, testnet, etc. Then from the message type, he can infer the message type from the command name itself, whether it's about version, whether it's about address, whether it's about the block, etc. Then the payload itself is also visible after this. So he can also, for example, if Alice is transmitting a full block, then the attacker can know about the contents of the full block itself, because it's clear text and unencrypted. And also the observer can make inferences based upon transaction announcement. So when a transaction is announced, he can uh, time or keep track of when a transaction is announced, when a transaction is requested, uh, and when a full set of transaction is sent by Bob back to Alice. So all these things an attacker can use to fingerprint Alice and Bob. For example, this pattern will be unique if Bob is a merchant and Alice is a customer. So the transactions announcement and request will be skewed or will be heavily weighted for Bob and than for Alice. So you can infer a bunch of things about a node based upon this kind of traffic analysis. Then with respect to a block, you can for example, if there is a if there is a command about block that Alice has requested, you can also learn a bunch of stuffs about the node, uh, whether Alice is a fresh node. If she's asking for historical blocks, you can very well be sure that Alice is a fresh node. It has recently been spun up, and she's trying to do IBD. So you can guess those kinds of information from the block message itself. Then when Alice and Bob, two peers, connect, they also exchange messages about their own peers. For example, if Alice is new and Bob is an old node, Alice will ask for Bob's peers, and Bob will be sending the IP addresses of peers that he knows, not just IP address followed. It can also be tar address, I2P address, what ports do these peers operate on. So all these kinds of information will be served by Bob to Alice. So this can also be observed by an attacker in V1. Uh, Also message direction. You The observer can cleanly spot in which direction message is flowing from Alice to Bob or Bob to Alice. Um, when you combine this direction along with information about uh, transactions and blocks, you can in general make a good profile about Alice. You can very well be certain that Alice is a new node. She's trying to do IBD, and also trying to Bob is an old node who is filling Alice in. So those kinds of information. And of course, you can also perform topological analysis on this. So the observer can sit in between and then gain a good uh, idea of the topology, as Bob itself will be serving a bunch of IP addresses, star addresses to Alice, and the observer can map the topology based on these information. So basically, these are the bunch of information that were exposed or that got exposed in V1 uh, transport protocol, P2P transport protocol version 1. So this was how Bitcoin P2P transport or P2P exchange was until BIP-324 became active. So it started development in 20, somewhere, I don't know, maybe I'm not sure about the exact date, but the BIP itself was accepted in somewhere in 2019, and I'm not sure about the version, core version, since it became active. So you can roughly think of 2019, somewhere in 2019, uh, when 3 to 4 started. In V1 was replaced with V2 transport protocol. So I'll pause a bit if there are any questions about what we have uh, covered so far. Yeah. So so next we'll look at how 3 to 4 works. So there are a bunch of stages to its working. Um, so we'll the first step is for a peer to discover whether for a node to discover whether its peer supports V2. Um, so typically, if your node has V2 capabilities, it gets marked in the service flag field that is associated with its own address that is stored. For example, if Bob is a known node, and Bob's address is IP address is this 203, so on, and his port is 833. Apart from these two information, the services that Bob's node offers is also recorded in the following fields: what sort of network it is, whether it serves you witness data, and also the new service field or flag with respect to V2 is node underscore P2P underscore V2. So if you set this with I think it's 8 bit, or I'm not sure about the total number of bits here. If you set it to 1 1, then it means your node supports um, this new BIP-324 protocol. So you typically set this node if you are if you have upgraded to the course version that supports P2P V2. So that is set, and this information is encoded into the along with the address, and it is kept in every node's peer directory. So when you do a handshake, you will know about whether Bob is able to communicate to you in P2P V2. protocol, and then after that, once you confirm this, then you go and establish the TCP connection. It's this establishing the TCP connection is normal. It happens either in V1 or V2. It doesn't matter. In this step, if there is no support, uh, if Bob's node doesn't support V2, then typically Alice will try to establish a TCP connection and talk to Bob over the V1 protocol itself. It's not that Alice will only listen to nodes with V1 V2 protocol. If V2 fails, and there is no service flag set, then Bob will try to connect with Alice over the V1 protocol. So once this is established, then comes the exchanging of ephemeral keys part. So this is the beginning of the cryptographic part of V2 itself. So first step is that what Alice generates, generates a random private key. This has nothing to do with transaction or wallet. This private key, it has only to do with the P2P protocol, not the Bitcoin protocol itself. So Alice generates this random private key. Then she derives a public key from it. Similarly, Bob generates a private key and derives a public key from it. So instead of sharing the instead of Alice sharing her public key with Bob and Bob sharing his public key with Alice, what they do is that they convert these public keys into a 64-bit alligators into a 64 byte data, which this process is called as ElligatorSwift encoding. This is just to make sure that it is not very apparent when some observer looks into this TCP connection. He comes to know that there is an exchange of public keys happening. So in order to avoid that, this encoding is done. So a rough overview of how this is done is shown here, but of course this is a lot more mathematically involved than what I have shown here. So typically a public key is taken, the X coordinate of a public key is taken here. Then a random field element is chosen. Uh, then a function that then the t value belonging to this function is computed such that it satisfies this equation here. So this function itself is a little more involved, what it is and all those things. So basically the operation is such that you find values of t such that if u of t equals your x coordinate of the public key. This is not an unique. This is not going to be an unique value. This t value. It is going to be. There's going to be multiple values of t that will satisfy this function. And what you do is that you randomly select one valid t, and then you serialize it as the random field element followed by the random the t value that you selected. So so this is the 64 byte encoding. So once this is derived, um, the Alice and Bob exchange the 64 byte Swift encoding. Once you receive this 64 byte Swift encoding, the Alligator Swift encoding is in such a way that the receiver can decode it. So there is a this is what we saw here is a encoding process. Similarly, there is also a decoding process. So the receiver can um, reverse this whole process and finally end up with the public key. So for example, if Bob receives the alligator Swift key of Swift encoded public key of Alice, then he can decode and get the X coordinate of Alice. So once he gets the X coordinate of Alice, he can further do processing with this public key. So so this is the Swift encoding, and here there is one more small sub process happening here before they exchange the 64 byte public keys. Um, uh, um, be, Before sending the 64 byte, uh, Alice can append to 4095 bytes of optional garbage data. This is in order to ensure that even this 64 byte alligator Swift encoding cannot be used as a fingerprinting mechanism by observers. So uh, so Alice, before sending this 64 byte out, adds or patches up it with any number of bytes of optional garbage, varies between 4095 0 to 4095, and then sends it to Bob. So so once Alice and Bob exchange their 64 byte alligator Swift key and decode their respective public keys, then they can go ahead and compute the shared secret using ECTH. So Alice goes ahead and computes her shared secret using Bob's private key, Bob's public key. Similarly, Bob computes Alice's his share using Alice's public key. So now this is the ECTH process. Uh, so so this share secret is further subjected to um, further subjected to uh, a process called as HKDF SHA-256 um, in order to encrypt the messages further. So till now, we haven't even touched the actual message that Alice and Bob wants to transmit. So now all that we have been doing till now is setting up a cryptographic system for Alice and Bob to encrypt the messages and share and then decrypt the messages between the two of them. So once you get the raw ECTH, you feed it into a HKDF SHA-256 process, and further using this process, you will eventually encrypt the messages. So, and also there is a system to make sure that Alice communicates to Bob about how how where the garbage byte ends. So 64 byte is a Swift key that Bob expects, followed by random number of garbage bytes. So, but Bob should know what will likely be the length of the garbage byte, so that he can identify what is the actual message there. So, so there is a handshake mechanism to ensure that Alice gives Bob the right length, all those things. So eventually, when you complete all these things, what happens is now Alice and Bob have the message that they want to send in an encrypted form, and now they can start transmitting via the TCP connection that they have established before. So that's what happens. Then in the meanwhile, they also keep rotating the encryption keys so that the encryption is robust. It's a kind of a feedback system or loop system that goes on, and they keep transmitting and receiving data between themselves. So this is a broad top level overview of how the BIP-324 system works. Next, we'll look at what are all the issues associated with this system, particularly with respect to quantum computers. So, if there are any questions in this process, please. I'll wait for a bit.
Bala, I have a question here that
Yeah.
what happens with the Alligator Swift public key? Like the shared key that they have created, which is SA and SB, that is
Yeah,
created from their initial keys that they have chosen, B and
yeah,
A.
yeah,
Uh,
yeah.
can you explain a bit about the role of this key?
Yeah, this is your normal
Yeah, this is
public-private
normal
key that
shared
is
key. Yeah.
shared. Yeah, the only reason why Alligator Swift encoding exists is to prevent sharing the public keys directly between Alice and Bob. So this encoding exists to make sure that you don't share 33 bytes of public key direct, because when this exchange happens, there is no encryption. So
Mm-hmm.
till we reach till we reach the secret computation and then the HKDF SHA-256, there is no encryption. Here in this part, particularly after deriving the keys, they have to share their keys between themselves, and
And
this will
A
be
and B.
done typically in ClearNet. So so in order to avoid revealing the public keys directly and
Mm-hmm.
avoid being profiled, this Alligator Swift encoding is used.
Okay, so instead of sending A and B, they actually send the 65-bit encoding of A, and similarly B sends the 64-byte encoding of B. Is that it? Hello, can you hear me?
Yes, we can hear you. Bala, we are not able to hear you.
Okay, okay. Bala, are you there? Shall I repeat?
I think we lost connection with Bala.
Okay, okay. I'll wait.
Audible?
Now you are.
Yes, you're
Yeah, yeah, yeah. Yeah, sorry. I lost you. I think when you say when you were saying about the exchange of 64 byte Swift
Yeah,
keys.
so I was asking that is it the case that instead of sharing A and B, capital A and capital B, they are actually sharing
Yeah.
the 64-byte Alligator Swift encoding of those keys?
Yes. Yes.
Okay. Okay, all right.
Yeah. Along with that, they also pack in a random
Garbage.
garbage byte so that even the 64 byte is not visible and is not, people can't fingerprint using this 64 byte.
Okay. So is it to make sure that it is quantum safe? Because if somebody does not have access to capital
Mm,
A and capital B.
no, till here the 3 to 4 protocol that exists now is not quantum safe. It
Mhm.
has problem. Uh, it has a problem. We'll look at where that problem currently lies. It lies in the ECDH process.
Actually.
So yeah, in the
Mhm.
ECDH process. This encoding is mainly to prevent deep packet analysis and getting to know your public key itself.
Okay. So if I directly send A and B, then they'll know which two people are communicating. Is that
Yeah,
the
yeah,
case?
yeah.
Okay. All right.
Yeah.
Thank you.
Okay.
Yeah,
So
about the
yeah.
sharing of public keys, this I think they're trying to simulate what happens in SSH or HTTPS.
Yeah.
But even there, when the browser is generating a new public key and sending it with the first packet, HTTP GET, the
Mm-hmm.
packet is then used to encrypt with that public key, and then the server sends his public key. So
Okay.
only the first packet is generally clear text. After that, there is no use of the public key because you can't use the public key to decrypt any
Yeah.
communication because both are sending it encrypting with their each other's public key. So now here, why is it a problem of leaking the public key? Because if they use that protocol which is established for 30, 40 years,
Mm-hmm.
they don't need to specially protect public keys because once the secure socket it's locked.
Mm, I am not very sure about that. Um, I'll have to look into it. Why, but particularly the alligator encryption, alligator Swift encoding is maybe um, it has to do with mm, um, uh, with the problem of uh, quantum threat, but I'm not sure whether in 2019 people were thinking about quantum threat and including um, Alligator Swift there. Mm, it's just an obfuscation format, and it's not an encryption. Um, but I'm not sure whether alligator encoding was done to obfuscate the mm, the public key so that quantum threats can be mitigated. That part I'm not very sure.
Yeah. Otherwise it's weird when when a protocol tries to obfuscate public keys because they can go in plain text. It is pretty useless to do
Mm,
anything public key because once a once a secure socket is established encrypting each other using each other's public key to encrypt data, nobody can do anything with it. So that's what's the weird part. Anyway,
yeah, I'm also not very sure why particularly alligator Swift encoding was chosen, and um, at least in the BIP it reads that it was chosen to make the public key look like an random set of 64 bytes. So that's the rationale that I came across in the BIP. But as you said, what is the harm in just sending the public key, because you can't do much with the public key. So yeah, the BIP at least reads that Alligator Swift encoding is used in order to make it not look like a public key. But why? I'm not sure. Uh, I'll have to read up more closely on the BIP. There should be some reason because there is a lot of computation involved in the part where you do the encoding and you do the decoding of the Alligator Swift uh, system. But I haven't read that part of the BIP closely. Maybe I'll get back to you after having a close look at it. So the
Bala,
quantum threat,
earlier
yeah.
your earlier explanation makes sense here that they might want to hide that who is sending the messages across this
Mm,
session that is established. So they might simply want to hide the keys, like the plain keys A and B,
okay.
and then they are instead using some other encoding to hide that public key. Um,
Hmm.
That
Yeah,
seems like
maybe.
an okay reason to do this.
Yeah.
It's nowhere protecting against the post quantum thing, because the final derived key, that is S, it is itself open to quantum threat. So
Yeah.
so
Yeah.
that's not the reason, I guess.
Yeah. 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 By 2019, I'm sure
Yeah, yeah, yeah.
quantum was not in the mind of people. Uh, so that is unlikely to be the reason. The goal appears to be to hide the appearance of the public key itself.
That
So
seems like a plausible
yeah.
reason.
So with respect to the quantum threat, so as we saw, the shared secret exchanges uh, before we took quantum into consideration, it used to go such that Alice and Bob exchange their public key like in the ElligatorSwift encoded format. Alice and Bob then decode it and then get each other's public key, and then they go ahead and compute the shared secret so that so that they have the shared secret. um, a passive observer and attacker, if he's a classical attacker and he doesn't have any quantum capabilities, he can't reverse the discrete log, and he can't derive Alice's or Bob's private key by observing any of these information. However, if the attacker is quantum capable, then if uh, he has a record of the alligator Swift encoding of Alice and Bob, then he can then he can decode Alice and Bob's public key, and from Alice and Bob's public key, he can derive their private key. And once he has done that, then he has the capability to uh, decode encrypted messages that Alice and Bob might share in between themselves, or he can even supplant himself as imposter and do a variety of attacks from there on. So this is the quantum threat that exists uh, in the existing BIP-324 protocol, P2P protocol. So this is why there has been attention paid to this particular area where discrete log is involved. So discrete log is not just involved in transaction signatures; it is also involved in the P2P layer, and I and people have started working on solutions for this. So whatever the news item in Optech newsletter 408 is related to a mailing list discussion about uh, the possible solution that can be used uh, in order to mitigate this problem. So the rough contours of the solution works like this. So you do the existing 3 to 4 handshake as you do normally. Then you enter into a temporary ECDH encrypted channel um, by sharing the typical uh, public keys between Alice and Bob, and then creating a shared secret and using that shared secret to encrypt the encrypt that particular channel. So once this ECDH encrypted channel is created, then you get into the ML-KEM exchange inside this channel. So what is ML-KEM is module lattice based key encapsulation mechanism. So it's a post-quantum cryptographic mechanism where two parties established a shared secret over the public network, but this whole thing is quantum proof. It's based on lattice cryptography, and it's a NIST standard, and it is quite it has been worked on quite extensively, and it is considered as mature. So once you do this, once you create this key exchange, then you create another actual post quantum encryption between Alice and Bob, and then you start the P2P messaging. So these keys are the new uh, ML-KEM secrets that you derived, and the keys that you derived using it, and the encryption that you created using these keys will be resilient to quantum threats. So this is the rough contour of the proposed solution. So I I I I I have very little understanding of ML-KEM, so I couldn't go into how ML-KEM works. At what I understood was the rough contours that is being proposed. So if you have any questions, or if anyone knows more about ML-KEM, please feel free to uh, add, add here.
That's one of the most difficult part of it.
Yeah, yeah. Some
I guess
way.
we cannot even cover that in one session, few
Yeah,
minutes.
at least we should, like, of course we can't do it in any one session, or even a series of session. We should slowly, I think we should slowly chip into these algorithms.
Although the name itself is encrypted. What to do with it?
Yeah. So just ML-KEM, you don't understand anything. Even if you decrypt it, you understand very little. Module lattice based key encapsulation mechanism. So that's another encryption within itself.
I guess this one is based upon the distance of a point from a particular coordinate system. So similar to we can have private keys
Okay.
corresponding to a point. You can
Mhm.
actually have multiple points within that frame of coordinates, which we used in
Mm.
this framework. So that is how the keys. I've not explained anything, but yeah, just to give an idea. So,
Yeah.
so the key is actually a point in that
And the cloud of
in the cloud of that coordinates, and you have to measure the
okay,
distance from that, and accordingly
okay,
derive the key. Something.
okay, okay.
Key is
So yeah,
not the point, but the distance actually.
okay. So yeah, it's
I know the
mm,
explanation is of no use.
yeah, yeah. Post quantum stuff's explanations are are of very little use.
Yeah.
So yeah, this was what I had to share today. The whole takeaway or summary is that um, we have quantum. We are using discrete log to protect a bunch of stuffs around the Bitcoin protocol, not just in transaction signatures. We also are using it in peer-to-peer communication. So, there is a problem there with respect to post quantum, and people have identified this, and are have started working on this particular problem also. Here I don't think it's much of a this people don't know about this because there is little scope for controversy here, and because you don't have to deal with at least that's what I think. You don't have to deal with a lot of memory constraints and other stuffs. I think you can have the liberty of choosing the best post quantum algorithm to serve this part as all this computations are handled by your node, and it doesn't have to be on the block itself. There is no space constraint involved, so there is little scope for controversy, and I think people can quickly settle on what is best, and then start implementing the solution here.